Welcome to the deep dive. Okay, so you know how it goes. You're trying to stay on top of things, get through your day, and bam, you stumble onto some fascinating research, this time about kids and how they learn math.
Hmm.
And you've sent over some really interesting material about executive functions and early math. Knowing our listeners, they want more than just the headlines. They want to understand what's really going on underneath.
Exactly. And that's what we're doing today, taking a deep dive into that very relationship between those core cognitive skills, the executive functions.
Like focus, memory, mental juggling.
Right, focus, holding things in mind, shifting gears mentally, and how children get started with learning mathematics.
And the thing that really jumped out at me was this piece from Educational Psychology Review, because it flags something that feels, well, it feels wrong, almost.
And so,
Well, there's tons of research saying these executive functions are crucial for kids learning math early on, like vital.
absolutely, a massive amount of evidence points that way.
But then, when researchers design programs specifically to boost those executive functions,
Yeah.
they don't always see kids getting better at math. It's like, huh, why doesn't that work?
That's the core of it. That's the puzzle.
Right.
So our mission today for this deep dive is to try and unpack that paradox.
Okay.
We need to look at the different ideas about how these things, EFs and early math, are connected.
And crucially, why some ways of trying to help might work better than others.
Exactly.
All right, let's start at square one then. What exactly are we talking about with executive functions? The article breaks them down, right?
It does. It focuses on three main interconnected processes. First up is inhibitory control.
Okay.
Think of it as your ability to focus your attention where it needs to be and, just as importantly, ignore distractions.
Like tuning out the noise.
Precisely. Imagine a kid trying to count blocks while the TV's on, or other kids are playing nearby. Inhibitory control is what helps them stay on task with the counting.
Got it. Mental blinders, almost. What's number two?
Second is working memory. This isn't just remembering stuff, it's like a temporary mental workspace.
Ah, okay.
You hold information there and you work with it, like remembering the numbers in a math problem while you're actually calculating the answer in your head.
Right, like mental math. You're holding the 7 and the 5 while you figure out it makes 12.
Exactly. That's working memory in action. It's got limited space, so it's about managing that effectively.
Makes sense? Holding and manipulating. And the third one?
The third is cognitive flexibility. This is your brain's ability to switch gears smoothly,
How do you mean?
like shifting between different tasks or different rules or even different ways of thinking about something. For a kid learning math, maybe it's switching from adding to subtracting or understanding that three dots are still three, whether they're in a line or a triangle.
Okay, so being mentally agile.
Pretty much. And the article stresses that while we talk about them separately, inhibition, working memory, flexibility in real life, especially when things get tricky, they all work together.
So they're this kind of cognitive toolkit. Kids need to, manage their thoughts, pay attention.
Exactly. And the article says they're seen as really fundamental for being ready for school, for learning effectively.
And it seems like it's not just about generally paying attention in class. The article really suggests EFs are tangled up with understanding basic math concepts, like number sense itself.
That's a key point. It suggests that sometimes difficulties with early math might actually stem from weaker EFs, not necessarily a lack of math understanding per se.
Interesting. So a kid might struggle not because they don't get numbers, but because they can't focus or hold the information well enough.
It's definitely a possibility the research explores, and this leads right into the next big chunk of evidence.
Mm.
This really strong link between EFs and how kids do in math, especially in preschool and the first few years of school.
A strong link. The article used the phrase vast body of work, I think.
It did. It's not just one or two studies. We're talking about a lot of research consistently finding this connection.
Can you give us a flavor of that, some examples?
Sure. The article mentions studies like one that found general EF skills in 3-year-olds predicted how well they did on both formal math tests, like counting, and informal math, like knowing more or less 2 years later.
Wow, from age 3, that's early.
Definitely. And other U.S. research showed that kids' EFs measured at the start and end of pre-kindergarten predicted how much their math scores improved over the following year. There's even UK research showing EFs predicting foundational math skills just before kids started formal school.
So it's consistent across different places, too. It really does sound like a solid predictor.
Very much so. The article cites quite a few others, Mulder, Ribner, Welsh, finding similar things. And what's really interesting and kind of hopeful
Yeah.
is research suggesting EFs might even help close early achievement gaps in math.
Oh, that's significant. So kids maybe starting behind in math, but with strong EFs, they might have a better shot at catching up.
That seems to be the idea. There was a U.S. study looking at kids in lower-income areas. It found that 5-year-olds who had good EFs, even if their math knowledge was initially weaker, sometimes caught up later with peers who started out stronger in math.
That's really powerful. So these EFs aren't just correlated, they might actually play a role in that trajectory over time.
Exactly. That long-term prediction, EFs at age 5 predicting math achievement years later, really highlights how important these cognitive skills seem to be.
Okay, so the link is clear, it's strong, it's predictive, which brings us right back to that original head scratcher, doesn't it?
Puzzle, yeah.
If EFs and math are so tightly connected, why doesn't training just the EFs automatically boost math skills? The article called this highly problematic.
It did, and it's a major focus. Despite all that correlational evidence, interventions that focus only on improving EFs often just don't deliver the expected math gains.
And these are the ones the article calls isolated EF interventions.
That's the term, yes. Programs designed to train EFs generally, maybe through computer games or specific drills, but without tying it directly to math content.
Like those brain training games that promise to make you smarter overall.
Exactly. And the article points to reviews and meta-analyses showing that the benefits from that kind of training often they don't transfer very well.
Meaning you get better at the game, but not necessarily at other things.
Precisely. Improvements tend to be narrow, specific to the trained task. The article mentions work on working memory training, for instance, showing it often doesn't lead to broad improvements in other cognitive areas or academic skills.
So a kid could get really good at a specific memory game on a tablet. But that doesn't mean they'll suddenly find it easier to count a big pile of objects or understand number concepts better in class.
That's the crux of the problem. Blakey and colleagues, mentioned in the article, even found that a computerized EF training program didn't improve preschoolers' math, even though EFs and math were correlated in that same group of kids.
Wow. So the link exists, but the intervention doesn't bridge it. That is puzzling. So what's the alternative then? As you mentioned, the article talks about integrated interventions.
Yes, exactly. These are contrasted with the isolated ones. Integrated interventions try to weave EF development into the math activities themselves. So you're not training EFs over here and doing math over there, you're doing them together. The article suggests this approach seems more promising.
That feels more intuitive somehow, like you practice focus while you're focusing on a math task.
Right. And the article also touches on broader curriculum-based approaches in preschool that embed EF development.
Like building into the whole school day.
Sort of.
Yeah.
These have shown some success in boosting EFs themselves, but the transfer to things like math skills is, it's variable.
Not a sure thing.
Not always. Some studies suggest these broader approaches might help certain kids more, maybe those from disadvantaged backgrounds or kids who struggle more with attention.
So context matters.
It seems to. But even some of those curriculum programs that look successful initially have had their effectiveness questioned later on.
So even integrating it more broadly isn't a magic bullet for boosting math specifically.
It suggests the relationship is complex. It's not just about having generally good cognitive control. There's more to it.
Okay, so this is where the article starts exploring the theories behind how EFs and math might actually connect, or fail to connect in those isolated interventions.
Exactly. It lays out a few ideas. One big one is simply mathematics demands EF.
Meaning you just can't do math without using these skills.
Pretty much. Think about word problems. You need focus. You need to ignore irrelevant details, hold information, put it together. That's all EFs.
Right, or mental arithmetic.
Absolutely. Holding numbers, manipulating them, it's working memory, switching between adding and subtracting or different rules. Cognitive flexibility.
It permeates everything, really.
Yeah. And the article brings in brain imaging evidence here, too. Studies show kids' brains actually work harder, activating EF-related areas more intensely than adults' brains when doing math.
Really? Why is that?
The idea is their math-specific brain networks aren't as specialized yet, so they rely more on these general executive control systems to get the job done.
Ah, like using a general-purpose tool before you get the specialized one.
Kind of. And interestingly, that difference in brain activity tends to decrease as kids get better at math. Their brains become more efficient.
So maybe that link is especially tight when kids are first learning.
That's another key idea. Early mathematics demands EF, even the really basic stuff preschoolers learn.
Like just understanding what 3 means.
Exactly. Cardinality, or
Yeah.
matching one number word to one object when counting one-to-one correspondence, these likely rely heavily on EFs too.
I can see that. You need focus to count each item once, working memory to keep track of where you are.
Precisely. Then the article broadens this out to EF as early cognitive contributors. This has a couple of facets. One idea is that EFs might be a performance limiting factor.
Meaning?
A child might actually understand a math concept, but their EFs aren't strong enough for them to show that understanding effectively.
Like they know how to count, but they lose track easily if there are too many items because their working memory gets overloaded.
Exactly. They can't perform the task successfully, even if the core concept is grasped.
So the EFs are kind of a bottleneck for showing what they know,
Could be. The other side of that coin is EFs as a learning facilitator.
helping them actually learn new things.
Yes. In this view, EFs actively help kids acquire new math concepts, using inhibition to ignore confusing non-numerical details when learning about shapes, perhaps, or using working memory to hold the parts of an explanation together, or flexibility to see how a number can be shown in different ways, dots, fingers, the numeral itself.
So EFs are involved in both doing the math and learning the math.
That's the argument. But the article adds a note of caution. We're still figuring out if the role of EFs is, say, bigger in preschool than later, or if it changes as the math itself gets more complex.
Right, the demands shift over time.
Exactly. Does algebra need the same kind of EF support as counting does? Probably, but perhaps in different ways.
Okay, this theoretical background really helps frame why those isolated interventions might miss the mark. The article circles back to that, right?
It does. It suggests maybe those isolated training programs only improve very general classroom behavior sitting still, paying attention broadly.
Which is good, but maybe not specific enough for math.
That seems to be the idea. Being generally attentive might not translate directly to the specific focus and mental manipulation needed for a math problem.
And crucially,
Crucially, these isolated approaches treat EFs as separate from math skills. But all the evidence we just talked about suggests they actually develop together, intertwined from early on.
so trying to train them separately goes against how they seem to naturally develop.
It appears so. It's like, as you suggested earlier, trying to improve dribbling by just wiggling your fingers. You're missing the context, the integration.
Right. The article also mentioned other factors, like maybe these interventions don't account for where kids are starting from in math.
Yes, that's another point. A general EF boost might not help much if a child is missing fundamental math knowledge, or if the quality of their regular math teaching isn't great. It can't compensate for everything.
So it's the whole picture, the child's skills, the content, the teaching, which leads us back, again, to the integrated approach.
Yeah,
That seems to be where the momentum is.
definitely. There's a growing consensus, as the article notes, that EFs need to be practiced within math activities. EF plus math, not EF then math.
Because you're targeting the specific ways EFs are used in mathematics.
Precisely. And there's even neuroscientific work identifying what they call mathematics-specific EFs. Things like paying attention specifically to numerical information, or working memory specifically for numbers, or being flexible with numerical ideas. These domain-specific EFs seem to be particularly strong predictors of math ability.
So it's not just general attention, but numerical attention, not just working memory, but numerical working memory.
Exactly. And researchers are actively developing and promoting these integrated approaches. But what's also fascinating is the idea that this relationship goes both ways.
How do you mean? Good math teaching helps EFs.
Yes. The article suggests that high-quality math instruction, the kind that encourages kids to think, reflect, and tackle challenges, can actually strengthen their executive functions.
So it's a two-way street. Good EFs help math learning, and good math learning helps EFs.
That's the exciting potential. Things like play-based math, social interaction during math activities, even just regular school attendance, these all seem to support both math and EF development.
That makes intuitive sense. A stimulating learning environment benefits cognitive skills broadly.
Mm.
But the article also tempered the optimism slightly. Right. saying the evidence for integrated interventions is still growing.
Yes, that's an important point of realism. While the integrated approach is promising, the results aren't uniformly positive across all studies yet.
Why the variation?
Well, these integrated interventions can look quite different from each other. How exactly they combine EF challenges with math content varies. We're still learning what works best.
So it's not enough just to mix them. We need to understand the mechanisms, what makes an integrated intervention truly effective.
Exactly. The article stresses defining the cognitive, educational, maybe even biological elements really clearly. The goal is to create that virtuous cycle we talked about.
Where challenging EFs within math makes both stronger.
Right. Think about that estimate count the dots example the article uses.
Yeah.
Just counting dots has some EF load. But if you add a challenge, maybe a time limit, or making the dots different colors and sizes mixed together.
Upping the ante cognitively.
Exactly. You're increasing the EF demand, needing more focus, more careful tracking, maybe ignoring the color distraction, while the core math task, counting, is still appropriate.
Yeah.
This pushes deeper thinking, maybe new strategies.
So you're deliberately making it a bit harder, cognitively, to encourage that EF muscle to work within the math context.
That's the idea. Viewing EF not as something that makes math hard, a performance foe, but as a learning ally. Strategically increasing the EF challenge, especially for young learners, might be key.
That's a neat distinction. Maybe for older kids who are struggling, you reduce the load, but for young kids learning foundational skills, you challenge it appropriately.
Potentially, yes, and neuroscience offers some support for why integration works better.
How so?
Well, in young kids' brains, those EF control networks and the math processing areas are still developing together. They're dynamically interacting.
So training them separately just doesn't match how the brain is wiring itself up?
It misses that crucial interplay. The article mentions interactive specialization, the idea that these developing skills actually influence each other's development in the brain.
Working together shapes both systems.
Seems that way. Plus, basic neurobiology, you need the right level of alertness, of arousal to engage EFs effectively during learning. Not too stressed, not too bored.
Sweet spot of engagement.
Exactly. And this brings us to the absolutely critical role of the educator.
Right. The teachers are the ones actually implementing this.
Absolutely. Their understanding of EFs, their ability to see EF demands and tasks, and their skill in designing math activities that embed these challenges appropriately. It's all vital.
And their expectations matter too, you said.
Hugely. If a teacher thinks certain kids just can't handle cognitive challenges in math, they might simplify tasks too much.
And unintentionally deny those kids the chance to practice and develop both their math and their EF skills.
Precisely. It underlines the need for really good teacher training, not just in math content, but in pedagogy and in understanding EFs and child development.
Knowing the what and the how of teaching, plus the how the brain learns.
You got it. The article gives the one program as an example, orchestrating numeracy and the executive.
Okay.
It's an integrated approach focused on trained educators embedding these EF challenges into play-based math. Their whole model is built on EF being that learning ally.
So it all really converges on this idea. Thoughtful, intentional integration within a supportive learning environment guided by knowledgeable educators.
That seems to be the key message.
Yeah.
So wrapping up this deep dive, we've seen that strong link between early EFs and math. Clear connection.
But also the real puzzle of why just training ES alone often doesn't boost math, the transfer problem.
Right, and the growing evidence pointing towards integrated approaches weaving those EF challenges into the math learning itself as a more promising path forward.
Because that seems to align better with how these skills actually develop together in the young brain, creating that positive reinforcing cycle.
Exactly. And the call from the research is for interventions with really clear theories about how this interaction works so we can refine these approaches even further.
This has been super illuminating. It really clarifies that disconnect and highlights why just adding a brain game might not be the answer. It makes you think, doesn't it?
Mm-hmm.
Maybe listeners can now think about the learning situations they see or even create. Are there ways, even small ways, to weave in little challenges, things that make kids focus a bit more, hold something in mind, think flexibly, all while they're doing the main task, like counting or following directions?
Finding that sweet spot of challenge within the activity itself.
Yeah. Could that be where the real magic happens for unlocking deeper learning in young kids? Something to really chew on.
A great question to ponder, and definitely worth exploring more resources on early childhood and the research itself if this sparked your interest. It's a really dynamic and important area.